is lecture 10G on the reflecting properties of the conic sections. Each of the conic sections have specific applications. The circle, these are in terms of physics, the circle is a pattern, say of radiation or gravitational field from a point source, assuming nothing else is bothering it. And that's circular pattern there. The ellipse, you see the ellipse in the Whispering Gallery. It's also used in lithotripsy. The orbits of planets about the Sun are elliptical, with the Sun at one of the foci, and comets that return periodically also have elliptical orbits. And for parabola, you're familiar with the parabola as a satellite TV receiver, also used as for transmitting antennas to direct the beam. And a hyperbola, the now I believe pretty much defunct LORAN navigation system used the hyperbolas. It was based on hyperbolas. Comets that appear only once generally have hyperbolic orbits, and the satellites, the flyby satellites, flyby space probes, those also have hyperbolic orbits. Most of these applications depend on the reflecting property of the conic section. So now I'm going to show you how to prove the reflecting properties of these conic sections. There's a lot of algebra here, just as there was in the previous two. Hopefully not as much, and the end result is more rewarding. The others were just different forms of equations that would be handy, sort of something you hope somebody else derives and puts in a book and you just use after you've looked at it once. But in this case, there's some insight to be gained, and also these properties, these reflecting properties, are very interesting. To prove these reflecting properties requires one particular result, and that result is right here. And we're going to derive this result, and then we're going to use it. This is the key to proving these reflecting properties. We're going to look at this construction right here. Alright, so we have two intersecting lines, L1 and L2. And the angle that they make with, in this case, a horizontal axis, is written as phi1 and phi2, but we're going to say theta 1 and theta 2. It doesn't matter, it's going to go away in a minute. Right. Now, there's an inner triangle here. The sum of these angles had better be 180. So these angles would be theta 1 or phi1 in the diagram, then the angle A, right, and then 180 minus theta or phi2, because that's an exterior angle, and of course we need the interior portion of it. We need the supplementary angle. We can rearrange this, and when we arrange it, we find that A is equal to theta 1 minus theta 2. Now I want to find the tangent of theta, or tangent of A. So A is theta 1 minus theta 2. Now I use the subtraction formula for tangent, one of these trig identities, okay, and you get theta, tangent of theta 1 minus tangent of theta 2 over 1 plus the product of those two tangents. Now what are these tangents? These tangents are equal to the slopes of these particular lines. So I can use M1, M2, those are the slopes of the lines, and rewrite the expression for tangent alpha in terms of those slopes. And this is the desired form. I've erased everything, and I'm going to highlight now the desired result. Tangent of A equals the difference of the slopes of the intersecting lines divided by 1 plus the product of the slopes of these intersecting lines. To prove these reflecting properties, we are looking at incoming and outgoing rays in terms of geometric optics. And geometric optics says that the angle of incidence equals the angle of reflection. We're going to show that the angles of incidence and the angle of reflection of rays hitting the edge of a conic section are equal by showing that their tangents are equal. We're going to start with the parabola. If you recall, the reflecting property of a parabola is that if any incident ray that would be coming, say, parallel to the axis of the parabola, when it hits the parabola, it is reflected. Here, it gets reflected to the focus. And that holds for any incoming ray. If you're using this as a transmitting antenna, any ray emanating from the focus hits the outside, hits a parabola, it will be transmitted as a ray perpendicular to the axis. So the green line is parallel to the x-axis. And we're going to show that this holds by looking at some arbitrary point P, which we'll say has coordinates P1, X1, and Y1, right? And we look at the line from the focus up to the point, and then we look at this line that is parallel to the x-axis, right? Right at P, right at this point P, there is a tangent, this tangent line whose slope is equal to the derivative at P, and we're going to use that. So here's our expression for the parabola, y squared equals 4px for this particular parabola, and we're going to use this that we derived previously. Tangent of A, here you see your A, but it's written as an alpha in this picture because I scanned it, and well, it's close enough. All right, tangent A equals m1 minus m2 over 1 plus m1 minus m2. So I've got to consider this angle and this angle. The slope of that tangent line, the line that was tangent to the parabola at P, is the derivative. For the parabola, we must use implicit differentiation. When we carry that out, we find that the slope of that tangent line is 2p divided by y1, because we evaluated it x1, y1. So we just used implicit differentiation. Right. Now the coordinates of the focus are p, 0. Okay, and so we want the slope from the line from the focus up to that point P. Here is m2. m2 is y1 minus 0 over x1 minus p. And now we're going to substitute and do a considerable amount of rearranging. We know this form. Tangent of alpha is m1 minus m2 over 1 plus m1 minus m2. After we do all this work, we find the tangent of alpha is 2p divided by y1. Now what is the tangent of that other angle, the angle between the parabola and the horizontal ray? That is just the slope of the tangent line, 2p over y1. The tangent of those two angles is equal. The angle of incidence then equals the angle of reflection, and this proves by geometric optics that the ray hitting the parabola will be transmitted out as a horizontal ray. Let's go back to the picture so you can see what we did. So here was one ray coming from the focus up to the point, or you could think of it the other way as transmitted from the point down to the focus, and here was our other incoming or outgoing horizontal ray, right, like that. Okay, these rays make angles alpha and beta with respect to the tangent line running through the point P. We need to show that alpha is equal to beta. We do that by showing that the tangent of alpha equals the tangent of beta, and since we know they're both first quadrant, or less than pi actually, then we can say that alpha does indeed equal beta, and we do it by showing that their tangents are equal. So what we did was used implicit differentiation right here to find the slope of this tangent line, right? And that would have given us one of the m's in this expression, right? Then we need the slope of the line from F to P, the green, and that's just done by looking at the point x1 minus x1 y1 and p0, so we just take the difference in y over the difference in x, and we get the slope there. We substitute it into this equation and we get one expression. Then we go up here and look for the tangent of beta using the same expression right here. In this case, the intersecting line is the tangent line, and we know its slope because we know the derivative. We computed that earlier. And then we need the slope of this incoming ray, which is 0. We found that the expression for the tangent of alpha equals the tangent of beta, and because of the constraints on alpha beta, we know that alpha and beta are equal. That shows angle of incidence equals angle of reflection, and that's what we wanted to show. Now we'll do the same thing for the ellipse. For the ellipse, a reflecting property says that a ray emanating from focus 1 hitting the edge of the ellipse is reflected to focus 2. That's a reflecting property of the ellipse. Again, we have alpha and beta. They are angles that these rays make with the tangent line through the point P. And we're going to use these two equations, this expression for the tangent of alpha equal m1 minus m2 over 1 plus m1 times m2, and we're going to show that alpha equals beta because these tangents are going to be equal. So here are the coordinates for the foci for an ellipse. F1 is at 0 and minus c, F2 is at 0 and c. Of course, we put the major axis right along the x-axis to make things easy. What are the slopes of the line? M1 is, just using the difference in y's over the difference in x's, M1 is a slope from F1 up to the point P. It would be y1 divided by x1 plus c, because c is oh, well, that is wrong, is it not? Okay. The coordinates here, need the pin. This is minus c and 0. They're located along the x-axis. This is coordinate is c and 0. Alright, now this is better. Okay. So now what is M2? It is the slope of the line from focus 2 up to that point, and it's y1 over x1 minus c. Difference in x over the difference in y. Or vice versa, rather. Difference in y over the difference in x. So it's just a straight line slope. Now we need to know the slope of the tangent line at the point P. That is equal to the derivative of the ellipse evaluated at that point. So we have to use, again, implicit differentiation. And here's the result. Minus b squared over x divided by a squared times y. Now we substitute into those expressions. We needed m1, m2, and we needed the derivative here evaluated at x1 and x2. And we do a whole bunch of rearranging, and we find that the tangent of alpha equals the tangent of beta. They both equal b squared times c over y1. Right. This is evaluated at x1, y1. Okay. And substitute it into those previous expressions. And then we find that the tangent of alpha does indeed equal the tangent of beta. We can conclude, because of the geometry, that alpha equals beta, so the angle of incidence equals the angle of reflection as we have set it up. Now we have hyperbola. The reflecting property of the hyperbola is that if this incoming ray hits some point in the hyperbola, it is reflected to the other focus. So it's similar to that. If the incoming ray that hits a parabola was aimed, I'm sorry, I didn't say the whole thing, was aimed at one of the foci, was aimed at F2, it will reflect off the hyperbola and go to F1. The procedure is essentially the same. We need the slopes of the lines from each focus out to the edge of the ellipse. The slope from the first focus is y1 over x1 plus c. The slope of the line from the second focus to the edge of the hyperbola is y1 over x1 minus c. They're similar, they're the same as the slopes for the ellipse. Now what is the slope of the tangent line? That would be the derivative of the hyperbola. Here's the expression for the hyperbola. Again, we use implicit differentiation and find dy by dx is b squared times x over a squared y. Evaluate that at xy, at the point P, xy. Substitute, do considerable rearranging, and we get the answer, same answers for the ellipse. The tangent of alpha equals the tangent of beta, which is b squared times c over y1. Thus, again, the angle of incidence equals the angle of reflection. They are equal, verifying the reflecting property of the hyperbola.